Okay, so now we're getting into three-dimensional supports. Cable, the forces have to be collinear with the cable. Smooth surface, force has to be normal. Roller, force has to be normal to the surface. Ball and socket, no moments. Like a pin, no moments. Forces can be on any of the three axes. Journal bearing, you can have a force, a reaction force um, in the XZ plane, but not in the Y, because a journal bearing, if you exert a force this way, the shaft will move. If you try to twist it, say around like so, you can have a moment on this bearing, or you can try to twist it in the XZ plane like so, and it can sustain a force. Obviously, if you twist it around um, if you have a moment in Y, M sub Y, if you have a moment parallel to the shaft, well, that would mean the shaft will turn. That's what bearings are all about. But and a journal bearing, it can slide. Okay. Um, Now, a square journal bearing, the purpose of this is to allow sliding only, so you can have moments around all three axes, but forces around only two of them. Because if you put a force in this direction, the bearing will slide in and out. A drawer glide is maybe the best example of that. Thrust bearings, that's like the bottom bracket on your bicycle. I rebuilt the bottom bracket on my bicycle, and um, to figure out how it worked. But you could have a reaction force along the axis of the axle. Along with it, like a journal bearing, though, you could have moments and forces along the z-axis, moments and forces along the x-axis. You can have a force along the y, but no moment, because if you had a moment, the axle would turn. Crankshafts on a bicycle, they don't slide back and forth. They go round and round. It's a thrust bearing. A pin, similar to a two-dimensional pin, you can have reaction forces in all three directions. Moments, if you try to put a Z moment, spin it around, like so, twist it, grab it in your hand and try cranking it counterclockwise. Or if you try to pull it towards you, you'll have a reaction moment. But if you try to spin it around the x-axis, it can move. So you can put a moment that causes it, to move this way or that way. Hinge, the same as your pin. Okay. Fixed support. You can have reaction. All six components of reaction forces and moments can exist with a fixed support. So we consider this, and we have bearings, and you don't have any rotation. Now they're also telling us something. When they drew the free body diagram, you could have moments. You could have a y and z axis moment at point A. You could have a z or x axis moment at point B, and you could have a y or x axis moment at point C. But this is the statement of the problem. This is a constraint you're given. For other reasons that we didn't calculate, or the designer chose a proper dimensioning or whatever, you don't have any couple moments. In general, you would. In general, you would. But when you're working problems from the book or homework, just watch out for things like this. And now we just have to solve for the 6 forces. And we have 6 equations, all the 3 moments equations and the 3 force equations. Here's another example of a bearing. We can have moments along the z-axis and the x-axis here, but not along the y, and forces on all 3, and then a tension in the cable and 200, and then forces acting on it. So we're trying to get all these we're trying to get the 5 reaction forces plus the tension. Here's another example. Again, the statement says no moments are developed at the hinge. So you can just draw the forces. And it looks like we have a journal bearing here. Yeah, a journal bearing. If it was a thrust bearing, you'd have an A sub y. Okay, 3D equations of equilibrium. So the sum of the forces has to equal 0. The sum of the forces in the x direction has to be 0. The sum of the forces in the y direction has to be 0. And the sum of forces in the z direction has to be 0. That's expressed here. Sum of the moments also has to equal 0, which is what gives us our 6 equations. Unsolvable systems. We already talked about what static indeterminacy is. There are more unknowns than equations. And you'll notice this statement here prevents static indeterminacy when the problem is stated. Improper supports. The body can move in 2 dimensions if the reaction forces are concurrent or parallel, and in 3 dimensions is if the reaction forces intersect a common axis or are parallel. And a door is a good example of that. Things that can move, like a door, have, quote, improper supports. Now, obviously, a door is very useful. You open and close it. It's intended to move. That's fine. But I gave the example when you grab the door handles and you try to lift up, you're exerting a moment, and there's a reaction moment that prevents you from doing that. If you grab the top of the door and the bottom and you twist left and right, one direction left and the other right, you're trying to twist the door. You're also generating a moment, but you have reaction moments that are equal and opposite, so you can't do it that way. Only if the moment is parallel to the axis of the hinges will the door move. Now we want to ask, so here's 3 situations. Good to illustrate improper supports and to ask, what are these all about? So we're going to have, back, come on. There we go. So we're going to have a force in this direction, a force in this, and a force in this direction, a reaction force. This is the applied force, not a reaction force. We don't have any other reaction forces. They do intersect at a point. So the system, this is improperly supported. Let's take a look at this one. We could have a reaction force here and a reaction force here. And the lines of action meet here. So also improperly supported. Here we have a reaction force here and a reaction force here. And it's a pin. So it looks a lot like A, but it's not, because we can have a third reaction force. These two intersect at a single point, and this one here will never meet this one here. So this one's proper. Okay. It's just terminology, by the way. So here's the answers. It gives you bar A or part A, improper. Part B, improper. Part C, proper. Okay.